Now we can look at some additional aspects of aqueous equilibrium. So we're going to look at, in this chapter, the common ion effect, some buffers, we'll do some titration problems, and then we'll look at some formation constants at the end. So in the common ion effect, it's basically just an application of Le Chatelier's principle, if you really think about it. So suppose you had just an acid ionization reaction. So we had acetic acid ionizing, so I'm going to add that to water. It's going to dissociate. We'll get some hydronium ions and some acetate ions here. All right, and so this is just a regular acid ionization reaction. You'll have a Ka that'll equal something. You can figure out how much of this acid actually dissociates into ions, how much of it ionizes. Now the common ion effect is saying that, well, what if instead of having just this in water, you actually had some of these ions present to start off with? And so if you have some of this to start off with, then when you're reaching equilibrium, so remember what your Ka expression looks like. I'll write down here Ka hydronium times this, so it's products over reactants. And don't worry about the water because the water's a liquid, so that's not going to go in there. Right? So you're still going to, the Ka is still going to be the same, but now you already have some of this to start off with. So the solubility of the acid, actually, not the solubility, the ionization decreases a little bit. And so this is saying the extent of ionization of a weak electrolyte is decreased whenever you have a common ion. This is common to this one. So let's see if we can add some math to this kind of problem. So basically the common ion is just saying that the solubility, if you have a solid, or the ionization will decrease whenever you have a common ion, an ion present already in your solution, because you already have one of your products there. So it doesn't have to ionize as much in order to reach equilibrium. All right, so this one says calculate the pH of a solution if you have 0.085 molar nitrous acid, and they tell you what that is, and they give you the Ka for this. So once you see the Ka, write the Ka expression, write the ionization reaction here. So I start off with this acid in water. I'm going to make some hydronium and some nitrite ions. And I know the Ka for this, so I know the Ka expression. Just write all that out there. HNO2. Okay. And that's a number. They give me the number there. And they say if you're starting off with 0.085 molar nitrous acid. You can make a little ice table here. The trick is that they're also telling you about some potassium nitrate. So where does that come into play? Where does potassium nitrate? That's your common ion. So the nitrite ion is what's common there. So potassium nitrite is a soluble ionic compound. It's ionic because it's a metal and like a group of nonmetals, right? A metal and polyatomic ion. And it's soluble because we know potassium is always soluble. So even if you don't know any rules about nitrite, you know a rule about potassium. All those group 1 metals are always soluble. So potassium nitrate, if you think about what's happening there, this KNO2, when you put that in water, it splits up into potassium and nitrite. So for every 1 potassium nitrite, you get 1 mole of potassium. Every 1 mole of potassium nitrate, you get 1 mole of nitrite. So I know what this initial concentration is here. So I have 2 initial concentrations. I don't have any hydronium, but I want to figure out how much hydronium I have because that's how I'm going to determine the pH. So I set up my ice table the way we usually do, minus x, plus x, plus x, and we're looking for x. We're trying to find how much hydronium we have. So just finish up your ice table, and then take that bottom row, plug it into your Ka expression, and Ka was what, 4.5 times 10 to the negative 4 is x. 0.10 plus x divided by 0.085 minus x, and life would be so much easier if we didn't have those x's on the bottom and the top, right? So all we're saying here is this number is pretty small, and we can confirm that. We can check the ionization later on to make sure that it's fine, that we don't need to use the quadratic. And so if this K is really small, that means this X is going to be small. So if I add 0.1 plus something really small, it's just 0.1. Or if I subtract whatever X is from this number, since X is so small, it's not going to matter. So I get rid of my x's, and then I can solve for x. For this x, don't get rid of that x. Then you'd get rid of all your variables, so you need that one. So we're going to do 4.5 times 10 to the negative 4. I'm going to multiply both sides by 0.085. Gives me x times 0.1, and then I can divide by 0.1. And I solve for x, which is the hydronium concentration, and that is 3.83 times 10 to the negative 4. And then you can find the pH of that. pH is just negative log 3.83 times 10 to the negative 4, and you get like 3.42 for your pH. So really the only new thing that we're adding here is that you have an initial concentration of one of your products. So you have an initial here, an initial there. Whatever Ka they give you, write that reaction. And then the other piece is going to be the common ion part. So you're going to have two concentrations. Scroll up a little bit. They give you two concentrations here and a Ka. Let's try another one of these. Very similar. Calculate the fluoride ion concentration and the pH of a 0.2 molar HF solution, so and 0.1 molar in HCl. So HCl is a strong acid, which means when you put that in water, it's going to split up into your hydronium, right, and some Cl minus. And the part that you really care about now is the hydronium. Sorry, well, covered up the Ka there. They give you the Ka for HF, and they give you the ionization reaction for HF. So this is a reaction that we're looking at. We're going to make a little ice table, and we have an initial concentration of the HF, and this is our hydronium, right? It's a strong acid. That's our hydronium, and we're looking for the fluoride ion concentration, as well as how much more hydronium do we make. All right, so we can set up our Ka expression. Always set that up. Over HF, great. And then you set up the rest of your ice table. Looks very similar to the last one, minus x plus x plus x. And here you have 0.20 minus x, 0.10 plus x, and x. And now you can take this and plug it in over here, and you get, what do we get here? 0.1 plus x times x over 0.2 minus x. And then just like we did last time, we're looking at this Ka, and we're saying that's small. Let's get rid of the plus x and the minus x. So we end up with 6.8 times 10 to the negative 4 is equal to 0.1 x over 0.2. And then we can multiply that through. Oops. Times 0.2 equals 0.1 x, and then divide by 0.1, and you get x is equal to about 1.36 or 1.4 times 10 to the negative 3 molar. And you can check. We didn't check the approximation last time. Let's check it this time. So if we had 1.4 times 10, this is our check to see if it's okay to eliminate that x and not use the quadratic. X over initial times 100. And I picked the smallest one. Since we're comparing, we have 0.2 and 0.1. If it works for 0.1, it's definitely going to work for 0.2. So pick the smaller one, and then you can check it that way, and this just comes out to be like 1.4%. So it's definitely going to be okay. That x is small enough that it's not going to affect anything. So this x right here is equal to the fluoride ion concentration, and then the hydronium concentration is just right here, right? So it's 0.1 plus this 1.4 times 10 to the negative 3, which we already said was really, really small. So our hydronium concentration is just 0.1, and our pH is negative log of the 0.1. which just gives us 1.00 as our pH. So we got our hydronium concentration, which was really kind of what we started with. We didn't really make that much more. And then the fluoride concentration. Make sure you don't stop here at this X and then try to do the negative log of that and figure out the pH from that. This is not the hydronium concentration. The hydronium concentration is whatever we started with, plus a little bit more, but since it was so small, it didn't really change the pH at all.